Okay, I wanted to create a quick video on the row space of a matrix. Before I do that, let's go ahead and look at a quick proposition here. I could have generalized this probably better, but this is specific enough you should get the idea of what I'm talking about here. Suppose that U is the span of these three vectors, U1, U2, U3. But suppose that the third vector, U3, is actually an element of the span of U1 and U2. Another way of saying that is U3 is actually a linear combination of U1 and U2. Then I claim that U is actually the span just of U1 and U2, so that you can go ahead and kick out U3. Okay? That should be pretty obvious here. I hope it is for you. But let's go ahead and go through a quick proof here. If U3 is an element of the span of U1 and U2, then there exist fixed scalars alpha 1, alpha 2, such that U3 is alpha 1 U1 plus alpha 2 U2. That's just saying what alpha 3 is a linear combination of U1 and U2. Okay, now what is the span of these three vectors? It's a set of all linear combination of those three vectors, right? So I'm writing it this way, A1 U1 plus A2 U2 plus A3 U3, where A1, A2, A3 range through what? The real numbers, right? Okay, this could be complex numbers too, but I'm just going to use the reals here. Okay, and I claim that's equal to the set of all u's such that what? A1 U1 plus A2 U2 plus A3, well, in place of U3, put in alpha 1 U1 plus alpha 2 U2. Okay, I just made that substitution then in there, like that. And then you guys see I can use the distributive properties that we have, fortunately, for vector spaces, and I can actually collapse this down into saying that U is what? A1 plus A3 alpha 1 U1 plus A2 alpha A3 alpha 2 U2. And then if you just think about it for a second here, if alpha 1 and alpha 2 are fixed real numbers, A1, A3, and A2 range through the real numbers, so do these numbers in parentheses. So I'll just go ahead and give them new names, B1, B2 here. Those are ranging through the real numbers, and therefore this thing is actually equal to the span of U1 and U2. Now you could generalize this statement, right, by induction, to make it a little more general than this. The point is, if you've got a set of vectors and you're finding the span of them, and you've got what, a vector or vectors that are linear combinations of the previous vectors written, you can go ahead and kick them out. Okay, there's no point in actually having them there. Okay, this is important in the idea when we're talking about subspace or basis for subspaces. Okay, here's the second proposition. Suppose that U is the span of U1 through UK. Then there exists some set B, which is a subset of U1 through UK, such that B is a basis for U. Okay, so B is a basis for U. So if you've got your space defined to be the span of a certain number of vectors, there's some subset of these vectors which gives you a basis. By the way, this is not necessarily a proper subset. If all of these vectors are linearly independent, in fact, the whole set itself will be the basis. Okay? All right? So this should be pretty clear from what I've done before here, but I'm probably spending more time on this than I need to. But let's go ahead and just to emphasize things, I guess. To be a basis, B must span U, right? Okay. And B must be linearly independent. Okay. No vector can be a linear combination of any of the others. Okay. All right. That's what it would mean to be a basis. Okay. I'm going to introduce some notation. This isn't necessarily standard. I don't think your book uses it, but some people do. Here's my notation. It looks like U is less than or equal to V. If these are subspaces here, or vector spaces, then this really means U is a subspace of the vector space V. Okay? So that is read in this context, U is a subspace of V. Now, that doesn't necessarily mean a proper subspace. They could actually be the same space. Okay? All right. U equals V means that U and V are the same vector spaces. Okay, that seems pretty natural. I've got U, what, a less than sign there? That actually means U is a proper subspace of V. That means what? There's vectors in V that don't appear in U. Okay, so V is actually bigger than U. Okay? Now I'm going to use that here in just a second here. Try and let the cat out. Okay? Let's go ahead and do this. Let's go back and we're considering this proposition, remember? Okay? Let's go ahead and let cap U1 be the span of U1. Okay, so that's just all multiples of that, right? Scalar multiples of that. U2 will be the span of the first two, so U1 and U2 vectors, okay? And so on and so forth, so dot, dot, dot. U, which is UK, right, is the span of all k of the vectors that I've used, okay? That's definitely, I'll call that U sub k in the context of this, but that's actually what we were saying U is, right? Okay? The following should be clear, that U1 is a subspace of U2, is a subspace of U3, and so on, all the way down to U sub k, which is U. Okay? Now, if any two of the subspaces in the sequence are actually equal, say U sub j minus 1 equals U sub j, then the U sub j vector can be dropped from the set of vectors forming the span, right? This would be a redundant vector. It's not adding anything new to the span. Thus, at each stage, the vectors remaining are linearly independent, and they'll end up spanning the space. Okay? Continuing this way until we reach U sub k, which is U, a linearly independent subset of our original vectors is formed that spans U. Let's illustrate what I mean here. Okay, suppose U is the span of these 7 vectors, U1 through U7. Okay, so U sub 1, okay, not as a vector, but this is a subspace, right? This is, whoops, that's got to have a bar on it. That's the span of U1. U sub 2 is the span of U1 and U2, etc. Okay, so we will go all the way down to what? U7. So we've got what? These subspaces of each other all the way down to U7, which is U. Okay, now suppose we have the following situation occur. U1 is a proper subset of U2, but U sub 2 is actually the same as U sub 3, right? So they're actually equal. They're not what? This isn't a proper subset of this one. It's actually an equal. Okay, but this is a proper subset of B4, but that's equal to B5, U5, which is equal to U6, but U6 is actually a proper subspace of U7, which is the whole space. Okay? Okay, then what would be a basis for this? Okay, what would be a basis for this using these vectors? Well, U1 we needed, right? U2, we got something new indicated by this, right? And we got something new. Don't need to put in the U3 vector because we didn't get anything new here, right? Okay, so forget that one. Oh, going from U3 to U4, the U4 vector was added, right? And that gave us something new. So we need the U4 vector. Nothing new here when we add U5, U6. Nope, nothing new. U7, we actually get an expanded space, right? So U7 is also part of the basis here. Okay, so this would have a what? A dimension 4 in this particular case. Okay, so that's just an illustration of what I did before. Now let's talk about the row space of a matrix. Suppose A is a real matrix with what? M rows and n columns. So an element of R to the what? M by n. Okay? What is the row space? The row space of A is the span of the rows of A and is written this way. Just row with A in parentheses afterwards. Okay? Row A is a subspace of all vectors in R. I'm going to write it this way. 1 by n, right? The space of all real 1 by n row vectors, right? Because if you're in a matrix and you're talking about a row vector has what? 1 row, but in this case, n columns, okay? So I would say R to the what? 1 by n. Now let me throw in a quick note here. We will often write R to the n to be the space of all real column vectors with n components, right? This has n components also, but this is a row instead of a column. But in the context of what I'm talking about here, in the context of column vectors versus row vectors, the notation n, R to the n by 1, would be, instead of R to the n, would actually be better, wouldn't it? Because this would be what? N rows in 1 column. Okay, that's what we really mean by a column vector. Okay, so we usually use this notation. But this would actually be better, particularly in this context. We haven't talked too much about row vectors, okay? Although you used what? Row vectors extensively in Calc 3, okay? That would actually, I'm just saying that's a better notation than that would be, okay? This is a little lazy here. But in the context, usually, you know, if I write something like this, that means you're talking about columns instead of rows. So this is just sort of a default position here. Let's take a quick example of a row space here. Suppose my matrix looks like this. A is 112, 103, 215 for the rows. Then the row space of A is just the span of those rows. So the set of all linear combinations of those three rows. Okay. By the way, I'm going to notice here that this last row is actually the sum of the first two. So this is redundant, right? So this is actually a redundant vector here. Okay, we don't need it when we're talking about the span. That goes back to our first page, right? You know, this thing. This holds for rows just as it does columns. You know, it doesn't matter. It doesn't matter how we write them here. It's still true. Okay, so the span of this is actually what? It turns out to just be the span of the first two rows. These are linearly independent. It's not hard to show here. Okay? And I just note that 215 is an element of the span of these two, so we can toss it here. And that's what I did. Okay? But that's just illustrating what the row space is for a particular matrix. Okay? In the above example, the first two rows served as a basis. In general, how do we find a basis for the row space for general A? Okay, for a general matrix A. Okay, and I'll tell you the answer, and I'll show you why it works here in a second. What you want to do is take A and write it in echelon form or row reduced echelon form. That would also be possible. And then I claim in the end the non-zero, almost forgot non-zero here, the non-zero rows of this form will serve as a basis. Okay? So what you want to do with a matrix like this is write it in what? Echelon form, and then take the non-zero rows, and you've got a basis for your row space. And I'll illustrate that right now with another example. So I've got this matrix A, a 4x4, 1, 0, 1, negative 1, 2, 1, 3, 4, 1, 1, 5, 11, 4, 2, 9, 14. Okay, I just went ahead and used the linear algebra toolkit online and got the echelon form for this. And here it is, 1, 0, 1, negative 1, 0, 1, 1, 6, 0, 0, 1, 2, and then the bottom row is zeros. Okay, so here, the row space of A, the set of all linear combinations of those rows, could be what? The span of what? The first three rows, the non-zero rows. Okay, so it's the span of the first three rows. Here's a little exercise for you, okay, because it's in echelon form. I mentioned this later. If you got it in echelon form, the rows are always, the non-zero rows, are always linearly independent. Okay, exercise for you. Can you see immediately that these rows are linearly independent? No row is a linear combination of the ones above. Should be pretty obvious here. Okay, but think about it. If you wanted to, instead of just using an echelon form, you could have used the row reduced echelon form of A. And I did that here, again, with the linear algebra toolkit. 1, 0, 0, negative 3, 0, 1, 0, 4, 0, 0, 1, 2, and then the bottom is 0. We don't need those. Okay, so the row space of A is the span of those three rows as well. Okay, so these lead to exactly the same subspace of, I guess it would be R 1 by 4. Okay, alrighty, so you get the idea. This is what you want to do. I might mention, since I'm not lying here, that the dimension of the row space would be the number of elements in the basis, right? But what is the rank of A? Okay, if I'm not lying here and you can do this, then the rank of A is the number of non-zero rows, and the non-zero rows serve as a basis, so the dimension of the row space of A has to equal the rank of A. So that's something you want to remember here. Okay, now I'm going to create a little notation here just to give you an idea why this is working here. Suppose my matrix A looks like this. Now I go R1, R2 down to R sub K. So there's going to be, in general here, K rows. I guess I could have used M here. Maybe that would be better. Oh well, I used K throughout. I should have used M. Anyway, Okay. Now, do you see what I'm doing here? This is my own notation. I'm going to say row vectors have a bar on top, but a bar on the bottom means that or a column vector has a bar on top. You're used to that. If it has a bar on the bottom, I'm going to say that's a row vector instead. So when you see these things, those will be row vectors, okay? The row space of A is going to be the span of these row vectors, R1 through Rk, which should have been Rn. Okay, which means what? It's a set of all row vectors such that row R is a linear combination of R1 through Rk. Okay, so these range through the real numbers there, the scalars. Okay, you know this stuff. Elementary row operations on A. Okay, so elementary row operations on A. Now just go ahead and reference this thing. Now look at it. Suppose I switch two rows. Okay, I don't care which two you switch. Say the first two. Okay, you switch those two. So R2 and R1 have been interchanged here. What's that going to do to the span? Nothing. Okay, it's not going to do anything. So it doesn't matter what order these vectors appear here. I'm going to get exactly the same span. So the elementary row operation on A of switching rows is going to change nothing. You're going to still retain the same row space, okay? All right, how about this? Multiplying a row by a non-zero constant. I claim that won't change the span either, okay? So that's the second type of row operation that we use. Okay, here's what I did. Suppose I had the jth row, and I've multiplied the jth row by a non-zero constant b here, okay? Now, remember that you're taking all linear combinations here, so there's going to be constants a sub j multiplying on the b r sub j together with the other terms here. Okay, well, b times a sub j is going to range through all real numbers just like a sub j was in the original, right? Okay, so do you see, I'm going to get exactly the same thing I got up here. I'm still going to get the row space, okay? So what happens here? The second type of elementary row operation, multiplying a row by a non-zero constant, is going to do nothing to what? The row space, okay? It's going to be exactly the same row space. How about our last operation? What's the last type of elementary row operation we use? Adding a multiple of one row to another row. I claim this won't change the span either. So here in the jth, I guess the ith space here, this is what I did. Suppose I took the ith row here, and I added a non-zero multiple, or even if it is zero, in which case you did nothing, but a multiple of the jth row and added it to the ith row here. Now r sub j is unchanged over here somewhere, okay, or over here, wherever it is. Okay, now go ahead and see that that's still the row space of A. That's still the same span I've got up here, because what? The A1 multiplies on the R1, the A1 multiplies on the B, Rj, but this combine with what? The other A sub Rj to just give you what? A1B plus Rj plus A sub j multiplying on Rj, and that's going to range through all real numbers again. So from the properties we have vectors, this is not going to give anything new either. Okay, yeah, I can write this ultimately just like that again, right, through the distributive properties. Okay, does that make sense? Okay, so what did we conclude? The third operation doesn't affect the span either. So what do elementary row operations do to A? As far as the span goes, they don't do anything. Okay, so you can imagine what if I'm starting out with a matrix A, and I continually apply elementary row operations, paying attention to what? The row space in each case. The row spaces are going to be equal all the way through. So when I get down to the echelon form, by a sequence of elementary row operations, we conclude that the row space of A is going to be the same as the row space of E. That could be R, the row reduced form, if you would rather, too, right? Okay, these are going to be equal. So there it is. I also claim what? The non-zero rows of E are linearly independent. That was the little quiz for you. That should be easy to see. And hence they serve as a basis for the row space. Okay, the non-zero rows, the zero rows, of course, you toss out. Those would not be part of the basis there. Okay, alrighty? All right, well, I hope you understood that.